So we are on page 9 of our packet. We've got 2 more days, today and tomorrow, to go before we finish the packet. This one uses very little, it still uses our trig identities that we've been looking at, but mainly the majority of this is algebra, okay? And we're going to actually be using some factoring as we go through, but it's much more heavy in understanding the algebra behind it than it is understanding the trig identities behind it, all right? If you look at the directions, this one says to write each expression in this factored form, and the key is as a single trig function, meaning you don't want it to be sine cosine. You don't want it to be cosine tangent. You don't want it to be secant and cotangent. You want it strictly all in sine, all in cosine, all in tangent, all in one specific trig function, okay? And however we need to manipulate the expression in order to get it into one trig function is going to be the key, all right? Then we're going to actually then end up in factored form, and we're actually going to need to be factoring it towards the end, all right? So we're going to start off doing number 43 and then 45, and then we've got a couple on the back that we're also going to do. So we're going to start here. So it starts off with cosine x minus 2 sine squared x plus 1. And here's my very elementary question I ask you. Is this expression written in one single trig function? And the answer is no, because I've got cosine and I have sine. We have a problem. We need to now look at the cosine and ask ourselves, using any trig identity, can I rewrite cosine, single cosine, cosine to the first power, as a sine function? So you pull out your trig identity sheet and you look at all the ways in which you can manipulate and look at cosine. Does any of them take us strictly to sine? And you look through that, and I'm going to answer it really quickly for you, and the answer is no. So I move over to sine squared. Can sine squared very simply and easily be written in terms of cosine? And the answer is absolutely. And I don't have mine right up there. The cosine squared can be rewritten as, here it is. Cosine squared can be rewritten as, where am I at? Cosine squared, I'm sorry, let me back up. It's sine squared that I want. So it's sine squared is equal to 1 minus cosine squared. So I'm going to replace strictly this. That's what's getting replaced. I had a great question third hour. And this is where I really love it when you guys are asking the questions, because you're giving me an insight into the way that you see it. I've done this for years. And so I almost get into like routine. But somebody said, well, can't you do sine squared plus 1? Is like, actually it would end up to be the opposite of cosine squared. Why can I not do that? And it has nothing to do with the Pythagorean identity. It has to do with this expression right here.
Because there's a 2 on the front of the sign.
There is a 2 on front of the sign, but that really does not affect why I can't do that, but that's a good point. How many terms do I have here?
2.
I have a 3-term polynomial is how I would word that. I have a 3-term polynomial. I can't just pull out sine squared plus 1 and say that that is a term. Poor cosine over here is going to feel left out of the whole party. Okay? But because sine squared is being multiplied by 2, and that's the only thing that I'm adjusting, I can just rewrite this in terms of 1 minus cosine squared. And that's what I'm going to do. So my first step is I'm going to take cosine x minus 2 times 1 minus cosine squared x plus 1. Everybody see where that substitution came from. Okay, off of our Pythagorean identity sheet. Okay, now what I'm going to do is I'm going to distribute this -2. I'm going to simplify this. So I'm going to distribute this -2 to everything inside that parenthesis. And I end up with cosine x minus 2, because -2 times 1 is -2, and -2 times negative cosine squared is a positive 2 cosine squared x plus 1. Because remember, sine, cosine, tangent, any of the trig functions, you can treat it just like as if it was a variable. So this would be like 2x squared. That means 2 times x squared. 2 times sine squared is what I have. And that's what I did right here. 2 times 1 minus cosine squared. So I just distributed that out. Da-da-da-da. Okay? Now, yes, Grant.
Never mind.
So now I've got a cosine squared, I've got cosine. I'm going to rewrite this in terms of standard form, meaning my degrees from highest to lowest. So 2 cosine squared x plus cosine x, and what's -2 plus 1? -1. Okay, everybody with me so far? First, I substituted in 1 minus cosine squared for sine squared to get all in terms of one trig function. And once I did that, I've got cosine and cosine squared. I don't care that one's squared and one's not, but they're all in terms of the same trig function. And this last step, I just rewrote it in standard form, where I've got cosine squared plus cosine minus 1, combining my -2 and my positive 1 to get the -1. Now, what I want you to be thinking, if this having trig functions in there is still a little confusing to you, what I want you to think in terms of is this. What I have is 2x squared plus x minus 1. That's basically what I have, where x is my cosine theta, my cosine x, okay? And now the directions, if you go back to what the directions are asking, they want it in factored form. They want a binomial times a binomial all in the same function. So I know I'm going to set that up in terms of binomial times a binomial. And I know that 2 is a prime number. So the only thing that I can multiply 2x squared by, or excuse me, the only two factors that I can multiply to get 2x squared is 2x and x. I don't have a choice on that. The last term is also a prime number. The only two numbers that can multiply to give me 1 is 1 and 1. But the problem comes, it's a -1. So I'm going to have a plus and a minus here, but I don't know where. And that's where you have to do a little bit of trial and error. So if I put a plus here and a minus here, lightly, because I don't know if that's really what it would be, this becomes, multiplying these two together, I get a -2x. This becomes a positive 1x. Does -2x plus 1x give me a positive 1x? Gives me negative. So I'm going to flip the sign. This is going to be negative, and this will be positive. So I get 2x, bless you, minus 1x gives me a positive 1x. And I'm finished. Okay? But I want it in terms of cosine, so I'm going to put 2 cosine x minus 1 times cosine x plus 1. And that's my final answer. Now, with that factoring being said, I don't have this up on the video, but on the board, I have our AC method that we went through and we factored all the way through. Step by step by step by step. And so what I just talked you through was a trial and error way in which to look at that. But on the board, and you're welcome to take a picture of it or whatever, but that is how to factor using that AC method, okay? The step by step on that, if you've kind of forgotten how to do that, okay? So, any questions on 43? All right, moving on to 45. 45, I have 4 tangent squared x minus 4 cotangent squared x. 4 over cotangent x plus sine x times cosecant x. I don't know why this, just a second, guys. Can you see it on there? That's what I want to do. Okay, here we go. So 4 tangent squared x, and now cotangent, and then I've sine and I have cosecant. I have 1, 2, 3, 4 different trig functions. Not nice. So here's a thought process. I want them all in terms of one trig function. The one above, fairly simple because I was just sine and cosine. But down here, I've got 4 different ones. So what, which one am I going to go for? So I'm going to go with here tangent squared. I know that tangent squared can be rewritten in terms of sine squared and cosine squared. But that still takes me to 2 trig functions. So I'm going to skip that for a second, okay? It also takes me to 1 minus secant squared. And that's really not helping me any. So I'm just going to hold on that. I'm going to move to cotangent. And understanding that cotangent is 1 over cotangent x, you pull out your trig function. 1 over cotangent is what? Tangent. Okay, now stay with me as thinking through this. 1 over cotangent is tangent. And that's 4 over cotangent. So 4 over cotangent would be 4 tangent. All right, so if I do that conversion, now this would be tangent and this would be tangent. Okay? I'm not saying that's what we're going to do, but this is our thought process. So let's hold on that. Then I have sine x times cosecant x. Say what? So I have sine x. Well, cosecant can be written in terms of what? 1 over sine. They cancel. And what's that equal? So if that's 1, can I keep the middle term as tangent and the first term is tangent squared? Absolutely. Okay, so what I have now is I have 4 tangent squared x minus 4 tangent x plus 1, all because of what I did right here. Okay? And what I have set up here, since 4 is a perfect square, 1 is a perfect square, I have a perfect square trinomial. Perfect square trinomial, which factors, and basically what you're thinking, what times what gives me 4? 2. What times what gives me 1? 1. And because that's a negative and that's a positive, they both have to be negative. And I have factored it. And you can, if you want, rewrite it in terms of 1 binomial squared. 2 tangent squared minus 1 quantity squared. But again, number 45, you could do the AC method. Obviously, the terms would be different that I have up here on the board. The process would be exactly the same. If you're confused with the little shortcuts that we did on 43 and then on 45 down here. Okay? Questions? Okay? Because 2 times 2 is 4. Those 2 have to multiply to give me that first term. Those 2 have to multiply to give me that last term. That becomes negative 2 tangent squared x. That becomes negative 2 tangent squared x. Those both add to give you the negative 4. So that checks. Okay, understanding what the first terms have to multiply to be, what the last terms have to multiply to be, the outside and the inside have to add to be that middle term. Okay, that's a mental thought process. If the mental thought process is confusing, go back to actually literally working it all out using the AC method. And that's a foolproof way in which you can use every single time. Okay? All right, flip to page 10, and we're going to do the top one. number 47. Now, we're still doing some factoring, and we're still writing into a single trig function, okay? So I look at 47, and I've got sine squared, and I've got sine, so I'm good to go. They're both in the exact same trig function. But before we get started, I just want to remind you of another factoring that we had. That if we have, let's say, a squared minus b squared. So if I have a first term that's a perfect square and a second term that is a perfect square, okay? First term's a perfect square, second term's a perfect square, and I'm subtracting. First term's a perfect square, second term's a perfect square, and I'm subtracting. That's called a difference of squares. Then I can factor it as a plus b times a minus b. That's just a given. That's just, you know that. Because when you take a times a, you get a squared. There's a negative ab and a positive ab. They cancel, but b times negative b gives you your opposite of b squared. Alrighty? Okay, so now let's look at 47. Knowing that I have 1 minus sine squared over 1 plus sine squared. Well, Mrs. Meyer, 1 minus sine squared x will get me to cosine squared. Oh, yeah, absolutely, that's correct. But for what we're doing here, that helps us not. What we're trying to do is get it down to one expression. All right? So what I notice on the numerator is 1 is a perfect square because 1 times 1 is 1. Sine squared is a perfect square because sine times sine is sine squared. So I have this situation here of a squared minus b squared. So I'm going to take 1 plus sine squared x times 1 minus, I lied, 1 plus sine, not squared, x times 1 minus sine x all over 1 plus sine x. Since the numerator has two binomials, but they're being multiplied together, that means those binomials can cancel. They're free to be let go. And since this binomial in the numerator is identical to the binomial in the denominator, they can cancel, and you're just left with 1 minus sine x. That is your final answer.
I like that one better.
That is your final answer. Now, if you look at 48, no, we're not. If you look at 48, am I in the same trig function? 48, same trig function? Yes. 49, same trig function? No. So 49 and 50, you're going to have to convert using a Pythagorean identity into the respected, the trig function that you see down in the denominator. But all those are going to be worked as simply as we did with number 47. Okay?